this video, we'll be discussing the second derivative test. The second derivative test is very similar to the first derivative test. The second derivative test is going to test intervals of the second derivative to see if the second derivative is positive or negative. When the second derivative is positive or negative, that's going to mean something, and it's a new term called concavity. In order to find these intervals, we're going to use what's called points of inflection. So by the end of this video, we'll be able to understand what intervals of concavity and points of inflection are, and we'll be able to use the second derivative test to find those intervals and points. So first, let's discuss points of inflection, or what I first start by calling possible points of inflection. Just like in the first derivative test, we had critical numbers, and critical numbers could turn into relative extrema if what's around it changed. Possible points of inflection are the same way. Possible points of inflection can become points of inflection if what's around it changes. Possible points of inflection, which I abbreviate with PPOIs, happen in two different ways, very similar to how critical numbers did, except we're looking at the second derivative. Possible points of inflection happen when my second derivative is equal to 0, or possible points of inflection happen when my second derivative is undefined. Now, what does that term inflection mean? Inflection means that something in the graph is changing. And that something in the graph that is changing at a point of inflection is what's called concavity. So these are the two ways that we can find possible points of inflection that will help us be able to identify intervals of concavity. What concavity is if you think back to when you did geometry, you heard the words convex and concave with the different shapes. And concave shapes were the shapes that could make caves. That similar word is here in concavity. There are two different types of concavity. The first type of concavity we'll talk about is something called concave up. Concave up are pieces in which the cave would be going upwards. So pieces that look like this. Now, the way I like to describe concavity is by pouring a pitcher of water from the top of the graph. In concave up pieces, if I were to pour water from the top of the graph, water would get stuck inside my graph. The second piece is called concave down. In a concave down graph, my cave would be going downwards. Or the way I think of it is if I poured water again from the top, concave down, the water would run down the sides. It would run off the sides. So try and visualize something like that happening. Now, very similar to how the first derivative talks about increasing and decreasing, the second derivative helps describe when my function is concave up or concave down. And concavity is described when my second derivative is either positive or negative. Concave up pieces happen when my second derivative is greater than 0, when my second derivative is positive. Concave down pieces of our function happen when our second derivative is negative, or less than 0. So let's take a look at a function and how we would use the second derivative test to identify intervals of concavity. So first thing we need to do is we need to get down to the second derivative level. So first derivative would be 3x squared. My second derivative, 6x. So what we need to do, again, is we need to find our possible points of inflection. Our possible points of inflection happen when our second derivative, 6x, is equal to 0 or undefined. 6x is not undefined because it is not a fraction. Undefined terms come in a fraction. So if 6x equals 0, that means that x could equal 0. Now, since we set our second derivative equal to 0 and solved for it, we're going to call this a possible point of inflection. It's not quite necessarily a point of inflection yet. We need to see what's happening around it. And very similar to the first derivative test, we're going to do our interval testing. We're going to create a number line with our possible points of inflection being that important number we're going to put on here, 0. And we're going to do our interval testing the same way. We're going to pick a test value. To the left, like -1, and to the right, like +1. And remember what we're testing. We're testing this time to see if my second derivative is positive or negative. So we're going to plug this value, -1, into our second derivative, which is 6x. When I plug a -1 into the function 6x, I get a negative term. When I plug a +1 in, positive 1 times 6 would give me 6. All I care is that it's positive. And again, the idea is that if I know something about my second derivative, if I know my second derivative is negative, that means that that piece of the function is concave down. If I know that that piece is positive, that means that this piece is concave up. And we should know what a cubic graph looks like. If I can sketch that idea, here's what a cubic graph would look like. It comes in through the origin and comes up like this. Notice, up until 0, we have a piece that is concave down. Then, right here, when x equals 0, it changes from being concave down. Now we have an interval that's concave up. So since what's around 0 did change from concave down to concave up, we would be able to describe that point x when x equals 0 as a point of inflection. No more possible points of inflection. Let's take a look at one more. Now this was another a function that we've talked about a little bit before. First derivative, 4x cubed minus 6x squared. Second derivative being 12x squared minus, I'm having trouble with that term, minus 12x. And we want to, again, always figure out when is our second derivative going to be 0 or undefined. In order to set that equal to 0, I'm going to factor out a 12 and an x, what they have in common, be left with an x minus 1, and set that equal to 0 to figure out when we have our possible points of inflection. So when x equals 0, or positive 1, we have our possible points of inflection. So if we were to look at this, draw your number line, put your points of inflection on here, your possible points of inflection, 0 and 1. We're going to pick our TVs, our test values. Negative 1 is a good one. Now in here I'm going to have to pick a value like 0.5, a fraction between 0 and 1. And then I can pick a 2. And remember, where we're plugging it in is to our second derivative. I could plug it into here, because that is my second derivative. Or I'm going to plug it into this piece, the factored version, because it's much easier for me to think of 12 times some number times some number. When I plug a negative 1 in, it would be 12 times a negative times a negative, which is going to become a positive term. If I were to plug 0.5 in for x, it would be 12 times a positive times a negative. Positive, positive, negative would make a negative product. When I plug a 2 in, 12 times a positive becomes a positive product. So when my second derivative is positive, that means concave up. When my second derivative is negative, that means concave down. And when my second derivative is negative, that means, again, concave up. So if I were to ask for the intervals of concavity, you would be able to describe this as concave up from negative infinity to 0, concave down from 0 to 1, and concave up from 1 to infinity. Now I just noticed that I didn't change my directions, so remember that we were looking at when the second derivative test to talk about not terms that were increasing or decreasing or relative extrema, but this time we're talking about concave up, concave down, and points of inflection. Since what's around 0 changed, this would be a point of inflection, and around 1 it changed from concave down to concave up, again a point of inflection. So let's quickly take a look at the graph of this. When I look at the graph, again, I should see a point of inflection. Let me flip back at 0 and a point of inflection at 1. So let's take a look at what happens when x equals 0. When x equals 0, that's right here. And when x equals 1 on my function, that would happen right here. And again, notice these pieces. Here's an interval of concave down. If I poured water from the top, water would get caught in that interval. Here's a, concave up. Here's a piece of concave down, and here goes it back to concave up. So you can notice that those intervals change just like we said, from concave up to concave down, back to concave up. So it's your turn to give this a try. Take a look at the function f of x equals 2x cubed minus 12x squared, and I want you to use the second derivative test to identify intervals of concavity and any points of inflection. Pause your video and come back in a minute to check your solution. So when you got down to the second derivative level, 12x minus 24, set that equal to 0. Get that x equals 2 as a possible point of inflection. And on your interval test, to the left of 2, you should see concave down because the second derivative would be negative. To the right of 2, you would see concave up, again, because the second derivative is positive. So we would identify interval from negative infinity to 2 as concave down, the interval from 2 to infinity as concave up, and since what's around 2 changed, we would say that when x equals 2, it is a point of inflection. So here we are at the end of the video. You, by now, hopefully know how to use the second derivative test to identify intervals of concavity and find points of inflection.